be talking about the significance of seismic evaluation for nuclear power plants. First thing is that there's been a constant updating of the loading spectra. Whenever we have had this major earthquake, the authorities have this, the rule that the seismic map of the country has to be redone. So based on that, we've been having this updating of the loading spectra. And over a period of time, we have had this evolution of the standards, the regulations, the rules, and the calculation methods. All of these have made or put the importance of the seismic evaluation to a different level. And till 2011, March 2011, when that Fukushima incident took place in Japan, many of us were not really aware of what could happen in the event of a nuclear meltdown. All of this has now emphasized the requirement of seismic evaluation of NPPs. Next, please. So to come to the type of seismic vibrations, first category is that there are certain events which take place in nature. One is whenever we have a tectonic variation under the earth, we have earthquakes, and whenever we have these magma following under the earth, we'll have these volcano eruptions. And as I mentioned, the word tsunami, the sad irony is that this is a Japanese word. Till 2011, as I said, nobody was aware, but nowadays, I don't know how many of you have observed, even the auto drivers and taxi drivers are familiar with this word. They put this on behind the vehicles, do not follow me, I am tsunami. So that's the kind of impact that's been made on the public. And microseisms are these mild murmurs, as they say, which takes place under the earth at a very deeper level. Next, and then we have these man-made events, explosions. These could be nuclear or chemical. And then whenever we have these huge dams and lakes, we have this reservoir seismicity. And many times we have read in the news that mines collapse and we'll have bursting within the mines. This results in rock bursts, which also give rise to seismic vibrations. Induced seismicity is when we have these huge drill rigs, especially in the oil and gas sector. And then we have these cultural noise, which is going up day by day. These are vehicular traffics and so forth. So before we start the seismic qualification, I would like to mention that this presentation covers only the natural phenomenon, that is earthquake. There are certain rules before we take up the qualification. All equipments in a nuclear power plant are classified into class 1, 2, and 3 based on their severity. A class 1 equipment is that equipment whose performance or the lack of it will directly impact the safety of the reactor and its auxiliary equipments. And the ASME section 3 is the one which addresses the nuclear parts. The subsection NB is the one which will be used for qualifying class 1 equipments, respectively NC for class 2 and ND for class 3. And the supports are to be qualified as per a different code, that is again section 3 NF. But before that, all equipments are also classified as passive and active equipments. Passive equipments are those equipments which do not have any relative motion within themselves. For example, a pressure vessel, a piping, these can be classified as a passive equipment. An active equipment is one wherein you have these where parts are moving relative to each other. For example, it could be a valve, a pump, a compressor, or a motor. So the difference between them is that passive equipments are to be qualified only for structural integrity, whereas the active equipments have to be qualified both for structural integrity and functional operability. The functional operability criteria will decide how the particular equipment will behave during the event of an earthquake. So there are different methods in which the structures can be qualified. The first one is the response spectrum method, which I'll be talking about today. And then there is this time history where you have the direct acceleration versus time. And then we have the equivalent static method, which is, you just take 1.5 times the acceleration value and you apply it as a static load, but that is applicable only when you have this cutoff frequency, a natural frequency above the cutoff frequency. Next, please. So this is a typical floor response spectra. This particular spectra is available at all different elevations of a plant. So that particular flow response spectra, which is corresponding to the elevation where the equipment is mounted, has to be used for qualification. This particular spectra will be different for the three directions. Say, for example, if the x is horizontal and we do not have the vertical direction, we can take 2/3 of the horizontal for the excitation. So the way this works is that we do a natural frequency analysis of the particular structure, and then based on the natural frequency analysis, we run this particular flow response spectrum or the response spectrum analysis. So those frequencies which are corresponding to the accelerations will be multiplied, and then all those results within the frequency of the spectrum, that is in this case it's 100 Hertz, will be brought together by using the CQC or the SRSS method based on the based on the spacing of the natural frequencies, how far or how closely they are spaced apart. Next. So these are some of the individual loads that the equipments are typically subjected to. This is the weight due to gravity, internal pressure, external pressure, temperature. These are static loads, and then we come to the dynamic load case, that is the OBE and the SSE. OBE here stands for operation basis earthquake. So this is that magnitude of the earthquake wherein the plant has to keep on running in spite of this particular earthquake being hit to the facility. The SSE stands for the safe shutdown earthquake. Even if the earthquake of that particular magnitude hits the facility should be in a position to be safely brought to a shutdown situation. So these are the different load combinations for which the equipments have to be qualified. The design condition is when the plant is not working, and service level A is when we have the normal operation of the plant. Service level B is when we have an earthquake of the magnitude of OBE, but we still have to keep the plant running. And service level C is when there is a situation wherein we have to shut down the plant. These particular load combinations are arrived from the plant operating guys. So on the last third and the fourth column, we see the allowable limits for the different class of the equipment. Here it says that NC and ND, that is class 2 and 3, is the same because we also have one more level, that is level D. But in the case where the SSE load can be taken in load C, load D can be omitted. So that's the reason why class 2 and class 3 have the same qualifying criteria. So this picture will give you a fair idea of how complicated a plant can be. This is a nuclear fuel reprocessing plant. So this has about 2,200 pipelines, about 45 to 50 vessels, and lots of nozzles, intersections, T-joints. So this particular equipment, structure will have hundreds of welds which are to be qualified. Again, hundreds of bolts of different sizes. So we devised a mechanism in which the pipes can be separated into bundles. That is, they were classified into their different parameters based on our studies. And then we have our own macros in which we can run the static loads and the dynamic loads, combine them. We have an automated system for that, and we also have an automated system for qualifying these particular equipments for different service levels. So this is one cable tray support structure. The reason for me putting up this picture is to differentiate the advantages of a software-based evaluation over a analytical way of design. The initial design was the one which was arrived from analytical calculations, and this is how it looked like when it was run through our FE codes. So this is as per the site requirements. This is heavily optimized. You can see that we have gotten rid of all the props that were there in the initial design. So this I don't think would have been possible in the place of analytical design, and also because of the size factor, I don't think you can even have this on a shake table or anything like that. Okay, this is again a 4200 kilowatt DG set weighing about 90 tons. The engine was shipped from Germany. The alternator was again from France, and the base frame was made in India. So we had to put all of them together, and somebody has to qualify it before it can be put into a nuclear power plant, and that's when we came into the picture. But because this is an equipment which is not classified in any of the ASMEs, this has to be qualified as per the manufacturer standards, and also the ASME codes of qualification did not hold good in this particular case because the load combinations were not as per the standards. So this was one of the load cases for the DG set where we had this load curve for 2 rotations, 720 degrees. So we had to analyze for every 15-degree rotation of the crank. That is, we had 48 load cases, and we had to pick the worst case scenario in order to qualify this particular DG set. Next. So as I said before, the load combination for this particular equipment was not as per the standards. And we also qualified the alternator for abnormal running condition, that is load case 6, where we have this immense load that is a reverse torque due to the short circuit load. Next. So this picture talks about the sloshing that is being captured inside a tank. During a seismic event, especially vertical tanks which are filled with fluids, they undergo sloshing, which could be even more detrimental than the earthquake itself. So we have arrived at this. We follow this particular method for evaluating the sloshing inside a tank. This is called as the Schussner model, wherein the pink springs represent the sloshing mass. That is the convective mass, which is the mass of the water which will be sloshing around, which will be connected by springs to the inner surface of the tank. The yellow one is the rigid links, which wherein the non-sloshing mass will be connected. The more about this particular concept can be had online, which is available freely. It's a paper which is jointly produced by one of the IITs in association with Gujarat State Disaster Management. So you can download that particular file, and you can get to see the equations in which all these are arrived at. So this is a waste nuclear waste handling tank, which is about 30 meters under the ground. The main picture, the reason of putting this slide is to show the complicated nature of the baffles and the intricate arrangement of the tubes which are at high temperatures inside the baffle. Again, for this particular tank, we had to do the nozzle, the sloshing, and the various nozzle loads which were coming on top of the particular tank. This is a lattice tower supported chimney which we did for our plant in Rawatbhata in Rajasthan. The end user had received a notice from the Environmental Pollution Board that some of their DG set silencers were not above the prescribed minimum height of 30 meters. So we went there to the site. Because this was a new design, we had to see the availability of the plates which we could make use of to design this particular structure. Again, a part of the structure was within the building itself, and then there was another part of the structure which was coming from the ground next to it. So we had to decouple the entire arrangement by using the decoupling criteria, and eventually we did manage to design this particular structure. it was finally erected, and our end user was allowed to run the plant, and the pollution control guys were pretty happy with this one. So in order to conclude my short presentation, I would say that seismic qualification is mandatory for all equipments before they are installed in a nuclear facility. Unless it's done, you cannot have your equipments inside. So ASME section 3 is applicable for the qualifications of these equipments. This is decided mainly on the safety class, that is the seismic class 1 or 2 of the equipment. And as I said, FE software provides a comprehensive assessment for qualification, because you can't really have every equipment put on the shake table. Even if you are putting it on a shake table, it will only say whether it's passing or not passing. But if you really want to know the margin, how close it can go till the allowable limit, and if you want to see the details of the stresses or the deformation in each and every part, you have to go with FE software. So the last 4 bullet points are our capabilities, where we have developed our own macros and scripts for load combination and qualification. In fact, we are also now working on ways to automate the report preparation, so that we can minimize human intervention, error, and also expedite the qualification process. So far in the last 5 years, we have successfully completed more than 45 projects on seismic qualification. These includes like hundreds of tanks and vessels and compressors, and many such. Practically, we have qualified every electrical and mechanical equipment. So in India, we are working with all DIE entities and their EPCs, namely NPCL, IGCAR, BRC, and with the leading EPCs like Punj Lloyd, L&T, and with many of their subcontractors. And we also did one overseas project, that is for ITER France through AMEC Nuclear, where we did qualify a section of the tokamak reactor, which is coming up in France, Cadarac. So with this, I would conclude my very short and quick presentation. Thank you.